How's everyone doing? Fantastic. I hope everyone's awake by now. And it's been an early start for me. So, right, okay. Proving the impact. Using synthetic control to evaluate the effectiveness of intervention. That's what I'll be talking about today. My name is Matheus Torquato. I'm a senior data scientist at JLR. At JLR, we are proud creators of modern luxury through our 4 brands, Range Rover, Defender, Discovery, and Jaguar. And our vision is to be proud creators of modern luxury, creating the most desirable luxury vehicles in the world. We are very, very proud of the vehicles we create. And our designs are a demonstration to our commitment to excellence and attention to detail. That's really important to us. So, right. Imagine a scenario that you're looking for buy your new or your second or your third JLR vehicle. You're starting your customer journey. So that's maybe one of your first views you're going to have, one of our showrooms. They look amazing. So yeah, that's a view in our showroom. You can go there, select your vehicle. And being very simplistic, but one of the ways we can split 2 ways that a customer can buy a JLR vehicle. So if you walk in, as you walk into one of these showrooms, you have pretty much 2 ways. The first way to buy a JLR vehicle is what we call a customer order. So in the customer order, you're gonna build the vehicle as you wish. You're gonna select everything. You're gonna make yours. And when I mention build your vehicle yourself, I don't mean this, even though this is quite cool. That's our partnership with Lego, the Defender here. That's the, Land Rover Defender with Lego. But what I mean about building your own vehicle is not this. It's more like this. So you can go to one of our website, for example, and customize the vehicle as you wish, selecting everything, all your preferences in terms of color, trim, engine options, interior, exterior, etc., etc. So this is how you can make, let's say, the first type of order, what we call customer order. Right, cool, happy days. And there is the second type, which is what we call a stock order, which is slightly different from the customer order. Of course, the customer order, as I mentioned before, you're going to spec the vehicle as you wish. This vehicle is going to be built. It's going to take some time. And then once it's finished, it's going to be delivered to you. Nice. Stock order works a bit differently. So in that case, you're not selecting all the characteristics of the vehicle as you want. You're going to walk into one of our retailers, which are third-party partners, and then you're going to select a vehicle that's already there, ready for you. So in that case, you're happy with this Defender in red, this engine, this trim, etc., etc. So in that case, you can take the vehicle straight away. That's the second type. That's a stock order. And it's important for the rest of the presentation to understand how this process of selling works. So we, JLR, again, making this a very simple example, but we, JLR, we don't sell usually selling straight away to the customers. We wholesale these vehicles to our retailers, and then they retail these vehicles to the final customers. So this is how it works. And then we have this question. So how can the retailers order the vehicles to better align with customer demand? Because imagine, I want a black Range Rover with that interior and that wheel. So how can the retailers anticipate this customer demand, my customer demand, to order this from JLR? And as soon as I walk into one of these retailers, I have this car waiting for me there, instead of placing a customer order, which is another option. So that's a very simple question, but the answer is quite complex. It's not straightforward. And I know it's not straightforward from experience. We know it's quite easy to fall in this trap, which is called the self-fulfilling prophecy, which is something that we want to avoid, ideally. So what is this? If you look at the bubble on the right, for example, let's start with this. We can start with any point. But let's start with this one on the right, which is there is a gap between the orders from the retailers and the actual demand. For some reason, the retailers, they order this vehicle, but it's not actually what the customers want. That's it. But then these vehicles will take, if you look at the bulb on the right, the vehicles will take longer to sell and sometimes even require some incentives, some discounts, because these vehicles are not selling as fast as we want. But that's due to the gap between the customer demand and these vehicles being ordered. So these vehicles are going to take longer to sell. In some cases, we need to discount them. Okay, they're going to take some time to sell. They will sell, and then that's going to be marked as sold in the data. And then in the review historical data and data-driven self-fulfilling prophecy, the retailers can say, oh, okay, that vehicle that we ordered, which was not what customers were expecting, it was sold. Yeah, it was sold, but because we had to discount, etc. But they will see just it was sold. That means it's good. Let's order it again. And then that creates a suboptimal historical sales interpreted as a real demand. And then these vehicles are going to be ordered again. And again, there will be a gap between the vehicles being ordered and the customer demand. Again, these vehicles will take longer to sell. Again, we need to put discount. These vehicles will eventually sell, not with the price that we wanted, but they will eventually sell. And you got the picture, right? And that's the self-fulfilling prophecy. And that is mainly due to two reasons. One is the lack of data available to the retailers. The retailers have, of course, their data available, but they don't have a wide visibility as we have, JLR. So that's kind of one cause for this issue. And also the complexity on the number of different configurations we have. So we have multiple vehicle lines. For each vehicle line, we have multiple trims and engines and interior and exteriors and colors, etc. So the number of combinations that you have to choose between to order your vehicles, it's absolutely huge. So imagine yourself being a retailer. How can you select the best vehicle to order to come next month so you can please all your customers trying to buy your new Jaguar Land Rover? So that is challenging, and that was the reason why this sometimes can happen. Right, so what is the solution for that? This beautiful project that we developed internally called Recommended Order Bank. For short, we call it ROB. ROB, Recommended Order Bank. So the point of ROB is an engine which takes historical orders for vehicles and recommends stock vehicles to be ordered for faster, more profitable, and more preferable cars for customers to buy. So in short, we're trying to minimize this gap between customer demand and what we are offering them. So that is ROB. That's a project that we developed internally that's currently recommending vehicles to our retailers. That, of course, uses artificial intelligence, uses AI. It contains 5 years of market and retailer history data. It contains more than 25 million data points, which is a lot. Each retailer gets unique recommendations. So if you think about a big country as the USA, for example, different retailers are located in different locations, one in warmer regions, one in colder regions, and each retailer has history according to the volume, the average value of the cars they sell, etc., etc. So Rob is able to recommend, make recommendations tailored to each retailers, and we also learn from similar retailers' histories to improve. So we're constantly learning based on the recommendations that we make, if these recommendations are accepted or not, and then what is the interaction between the retailers. So we developed Recommended Order Bank, Rob, to kind of solve the self-fulfilling prophecy. Perfect, good. So what you can see here is a plot. Wow, yeah. So on the x-axis we have time, on the y-axis we have a variable that I'm calling here y. And then in blue you can see the actual values of this variable. So let's think about this variable y being anything very important to our business. It can be customer satisfaction, it can be variable profit, It can be the number of days a car takes to sell. In that case, we're trying to minimize this variable y, but we have y. These are the actual values. And that, in this vertical line, you can see the intervention. So that's when we implemented ROB. So that's when we started recommending these vehicle configurations to our retailers, yeah? And then you can see a significant change during the post-intervention period for the variable y. These are the actuals in blue. But the question is, how much of this effect is due to ROB? Can we calculate the effect of this intervention? Was this just by chance? And what would have happened if we had not implemented ROB? Would have been in B, in A, where? So that's the question we're trying to answer here. So that's the main point of this whole presentation, to measure the impact of interventions. In this case, this intervention is recommending vehicles to our retailers, is the implementation of the recommended order bank project. So to measure this, to measure the success of specific projects, it was quite straightforward for us in the past. So we had these business methods defined by someone in the business, maybe finance, that they use to calculate mainly monetary return for specific projects. And that worked fine until COVID. COVID hit quite hard. It changed everything. It changed all the scenarios that we knew how to navigate. It changed dramatically the volume, the supply. It changed everything. So it kind of posed a challenge to the methods that we were using before. And as this was not enough, it came the global semiconductor shortage. I don't know if you know, but we're still suffering a bit with this, not only JLR, but all the automotive sector. We use a lot of computer chips in our vehicles. So this was another thing that changed dramatically the scenario that we were in. And yeah, so for those reasons, we kind of move away from the methods that we were using at the time. But we still had to calculate the value of this project. How can you continue or discontinue or expand this project if you don't know how much value it's delivering? We know that the gold standard for calculating the causal effect of a treatment is A/B testing. So that was option number one. But of course, A/B testing in this case was not applicable. A/B testing, of course, has some requirements. And these requirements did not fit the scope that we had at the moment. So for example, random assignment. In that case, we started recommended order bank. We started recommending vehicles to a single market. We sell vehicles to multiple markets. But in that case, we started applying this intervention to a single market. So we couldn't have this random assignment. And there was also something in the past. So we couldn't tune the A/B test as we wished to actually perform this test and calculate the causal effect. So that's why I actually added this here, because I did this presentation before and everyone asked about A/B testing at the end. So I put it here just to make it clear that we tried A/B testing and it didn't work for the scenario that we had. So that's why we had to move to synthetic control, which was the tool that worked perfectly for us, given that scenario that we were in. So here, that's a non-exhaustive list, but just a few requirements for applying the synthetic control method, which is the availability of comparison group, which we had. So we applied the recommendation to a market, but other markets were not receiving this recommendation. So we had this control group. No anticipation. So we didn't see any effect of this recommendation before starting recommending them. So let's imagine if the government wants to put a new tax and they're going to apply this tax by December this year, but they announce they're going to apply this tax tomorrow, there can be some effect before the actual intervention happens because of this anticipation. So that's something really important and that we need to consider when applying synthetic control. And sufficient pre-intervention information that we also had, that pretty much was everything before the intervention. So cool, we decided to use synthetic control to basically answer to this question. I've mentioned that before, but what we're trying to answer is what would have happened to Y, Y being, again, customer satisfaction, variable profit, any important KPI. What would have happened to Y if we had not implemented Rob, recommended order bank. So this is the question we're trying to answer here. And then we use syntactic control. Have anyone heard about syntactic control before? 1, 2, 3, 4, 5, going up like popcorn. Right, cool. So this is kind of short definition of syntactic control. It's a statistical technique to evaluate treatment effects in comparative case studies. It creates a synthetic version of the treated units by weighting variables and observations in the control group. So we have a control group, we have the target group, the group that's suffered the intervention, and then we create a weighted average of the control group to try to to mimic the values of the other one. That's going to be clear very soon. But syntactic control is really, really powerful. It's being used quite a lot, and it's getting more and more attention with time. It has even been described as potentially the most important innovation in the policy evaluation literature in the last 15 years. And that was not me saying. I've got a reference here from, what was that? Journal of Economic Perspectives. So yeah, it's something big, and it's getting more and more attention. And it's being used to calculate the impact of some big events, such as Brexit, the B word. Right, so what you can see here on the right is the synthetic control version of the UK economy based on this order market. So what we're trying to answer here is, what was the impact of Brexit in the UK economy? That is the question we're trying to answer. So what you can see in blue, this is the value, the actual values of the UK economy, right? That's in blue. And in red, that is a synthetic control version of the UK economy. So you can see the first vertical line, that's the referendum. The way to calculate this synthetic control is using the pre-intervention period. We can use contributions from these other markets, these other countries, units from the control group, to try to mimic the behavior of the UK economy during the pre-intervention period. So in that case, you can see that the blue and the red time series, they're quite similar. That was the purpose. So we can say that the synthetic control version of the UK was composed by 20% of the UK economy, plus 30% of the German economy, and X% of the Australian economy. So you got the picture. So by using different ways, if you go back to the definition here, if I can, it creates a synthetic version of the treated units by weighting variables and observations in the control group. So our control group here in this case are all of these nations not affected by, all of these nations not directly, that still doesn't work. All of these nations that were not the main target of Brexit, and these are the control groups. So we use these nations to calculate the synthetic control version of the UK variable of the UK economy during the pre-intervention period. So once that's done, we have a recipe, we have a formula to replicate the behavior of this UK economy during the pre-intervention period. And we assume that we can do the same for the post-intervention period. So once we calculated this formula during the pre-intervention period, we can just extend this formula to the post-intervention period, and then you see a gap between the actuals and the counterfactuals. So what you can see here, this gap is the gap between the actual values of the UK economy and the synthetic control version of the UK economy. So this is the effect of the Brexit in the UK economy, and the researchers from the Centre for European Reform, they concluded that by the end of 2021, UK economy was 5% smaller than it would have been had we stayed in the EU. We're not getting political here, but that's what the researchers concluded, right? We've been 5% better off if we had stayed in the European Union. So that was one application of synthetic control. That was not us, just these researchers here. But I think that's a very, very nice example. Right, so that's one example. Now let's jump on what we did at JLR, which is something very, very similar. So that's why I gave the example. How am I doing with time? Okay, I'm good. So this is us. Again, Y variable. Let's imagine here Y a variable that we want to maximize. So let's think about profit. And here we have the Y variable for different markets. So we sell for different markets. And we have there the intervention in Rob when we started recommending vehicles, but let's keep in mind that we started this project, we started this intervention just for a single market. So we initially started recommending vehicles just for the USA market, and we have all of these other markets not affected by this intervention. Nice. So what we're doing now, we are calculating the synthetic control version of the Y variable for the USA market. And here, very similar to the Brexit scenario, I'm using 23% contribution of the Y variable from India, 13% of contribution of the Y variable from South Africa, 22% of Brazil, 42% of the UK. And then you can see we're trying to match the actual behavior of the USA Y variable during the pre-intervention period, and try to match that as close as possible by using different contributions of different units in the donor pool. That's what we call the donor pool, the control group not affected by this intervention. Of course, we want to make those two curves on the top as close as possible, but we need to be careful to not overfit that, as we want later to expand this to calculate the effect. But that's what we have. It's really nice because it's kind of explainable, so you can see the different contributions from different units. So, for example, UK has a 42% contribution, so we can clearly see that the UK is the unit that resembles the most with the behavior of the USA. And then now that we've calculated this synthetic control, we have a formula, we have a recipe to mimic the behavior of the Y variable for the USA market. So once that's done, that's most of the work done already. Good, and then we can expand this formula, this recipe, to the post-intervention period. So the idea is, India, South Africa, Brazil, UK, they were not affected by ROB before the intervention. They're not affected by ROB in the post-intervention as well. So if you use this formula to calculate this divider that mimics the Y variable of the USA, the Y variable of USA, during the pre-intervention period, it should be fine to have this value for the post-intervention period as well. So now we have post data for actuals and the counterfactuals, the synthetic control, and then we can see a gap. Interesting. So the actuals value is higher than the synthetic control version. And the synthetic control version is pretty much saying, okay, this is what would have happened to the Y variable in the USA market if you had not implemented that intervention right there, the recommended order bank intervention. And if you remember, I said the Y variable is something that we're trying to maximize. So this gap is the result of our intervention. Not increase. If we had not made that intervention, we've been in that level, the level below, but the result of this intervention is the gap between the actuals and the scenario where I had not implemented this recommendation. So this is how we use that control to calculate the impact of specific interventions in projects in JLR. But of course, this is dummy data. I just made up these numbers and these countries and pretty much everything. But I can show you real data. So that's our real data. So that's the actual data that we try to match and to build the synthetic control. Unfortunately, I had to remove all the labels here, but I can tell you. Orange is our real data. The big difference here is that we're not trying to maximize anymore. We're trying to minimize. So instead of thinking as Y as variable profit, a variable we're trying to maximize, you can think as Y as days to turn is a metric that we use, which is the number of days a vehicle takes to sell. So if the retailer is buying the vehicle and that vehicle takes 2, 3 days, 5 days to sell, that's way better than taking a month. So we measure this value here and we try to minimize this value. So we have this in orange, and then in blue, that's the synthetic control version of this variable for that specific market. Of course, we have these bands for the confidence interval. But if you look here at the post-intervention period, you can see there is a gap again. And now the actuals are below the counterfactuals, below the synthetic control version, which means this intervention was positive, was what we were looking for. So even though if you consider the the confidence interval, we still have a gap between the orange curve, which is the actuals, and the lower band of the confidence interval, which made us really, really happy. Because if you remember, we had the problem that we were having problems on calculating the impact of certain measurements. But by using this technique, by using synthetic control, by using causal inference to calculate this impact of certain interventions, we were able to convince the business to prove the impact, to give numbers, specific numbers, to this project that we delivered. So we can, after that, we could convince the business internally to say, hey, by implementing recommended order bank, we delivered that much, and that can be calculated not only from monetary values, but we can say we increased that much profit, we reduced the number of days a car takes to sell by that much %, and that's just a summary of Rob here. So one of our most important metrics that we calculated is this. DTT, as I mentioned before, is the days to turn, is the number of days a car takes to sell, and reduce that by 20% by, instead of relying on guts, rely on these recommendations that we did using artificial intelligence, that many data points, etc. So we were able to reduce DTT by 20%. The recommendation that we are recommending from Rob, we're doing a lot, so this number is probably much higher, so around 8,000 recommendations. We saved a lot of time as well during the order calls. Order call is a activity that the markets, they batch order vehicles from time to time, so that is a process that takes a lot of time, but by using Rob, we're saving lots of time and all the important metrics here. By also proving the impact of recommended order bank, we were able to convince the business to expand and recommended order bank to different markets. So we initially started just with the USA. Now we are recommending vehicles using Rob to China, Canada, South Africa. We're starting to do it for the UK now. We're gonna expand to Europe very, very soon. We have a metric for acceptance rate, which is the percentage that the retailers accept of our recommendations. Of course, they don't accept everything, but they accept a great portion of it. But yeah, so that was the magic of synthetic control. We were able to prove to these internal stakeholders and the business that we actually delivered value. And believe me, that's not easy. But by using this scientific technique, using numbers and causal inference, we were able to prove and expand and get that project accepted and expanded. So that's what we did using synthetic control. And that is everything that I had to share with you today. Happy to take any questions. Thank you.
So for the questions, if you can raise your hand, and I'll come around with the mic and you can ask. So we'll start with the gentleman at the back.
Hi. Oh, hello. How do you account for something like COVID that might impact sales by market? I imagine the weightings over a period like COVID might be different to a period after COVID. So do you just remove that from the pre-intervention data set, or how do you do that?
Yeah, so in that case, COVID is something that of course, it's one assumption, but I think that's a similar assumption to other techniques for calculating impact as well. We assume that the effect of COVID was equally distributed along all the markets. So, of course, COVID affected the USA, but also affect India and Brazil, et cetera, et cetera. So we believe that these factors are already embedded in the synthetic control version, since it affected pretty much everyone equally. That's long shot, but that's a stretch, but that's the assumption.
Thanks, Matheus. Great presentation, by the way, about synthetic control groups. What packages have you used, and what languages have you used as well?
Package, none. Language, Python. But that's not really relevant. We are aware, after we finished doing this project, I looked around and I saw that there are many libraries for synthetic control. I've started experimenting with them, but the hard work we did was pretty much all manual. Which, to be honest, is not a big deal. It's pretty much trying to fit two curves based on the different baskets of markets. So that's not impossible. It can be done without a library. It's fun.
Hi, thanks. Great talk. Just have a question about the graph that you presented. So I noticed that there is a divergence even before the recommender is set up, right? So I was just wondering, how do you account for a divergence, and also later on, how do you actually validate your results before you present that to your internal business stakeholders?
So yeah, you're talking about this here, this divergence right before the intervention, and that's something that got us talking and thinking about it for weeks, because we thought there was a anticipation of the result, but there was actually just a difference between the actuals and the synthetic control. You can see there are differences all over the place. We always been careful to not overfit this. So we assume that was just another normal distance, as you can find in any other part of the pre-intervention period. Sorry, your second bit of your question was?
It's like, how do you validate your results? Like, I know there is no run-through in causal inference, but like, how does that add to your confidence before bringing that to a wider system?
Yeah, so that's a very good point. So to validate this, we actually calculate the synthetic control version for all of the markets, including the markets not affected by this intervention. So for example, the idea is we have, let's say, the USA market, it was affected by this intervention, so we expect to see a gap between the synthetic control and the actuals, and we calculate the synthetic control for all the other markets. So let's say I'll calculate the synthetic control for Germany, but Germany was not affected by this intervention. So I expect to see the difference between the actuals and the synthetic control, no difference, it should be the same. So if I calculate the synthetic control for all of the markets that we have, and we see that clearly the biggest difference is in the market affected by this intervention, that gives us confidence that the results that we have is not by random chance. It's actually derived from the interventions that we did.
Hi, over here. Can you talk a little bit more about the weights? So you mentioned that you assigned a greater weight, for example, to the UK because the economy was more similar to the United States. But I'm just wondering, is this something that you calculate, or is it an iterative process? And then also, you know, how susceptible to these weights? You know, do you have to fine-tune these, and does the result vary a lot or not?
So, yeah, these are calculated values. So what we're trying to do here is to minimize the gap between these two curves on the top. So what is the best formula, the best recipe that allows us to mimic the y variable of the USA as close as possible? So we put this in a regression, in optimizer, whatever you want to use, and then this is the weight that we used. There was the second part of the question. My memory is really short.
Yeah, just how susceptible to these weights that you select or that you calculate, how much does that affect the synthetic result at the end? Like, do you have to cross-validate or something like that?
No, so a few things that we had to adjust before was based on other markets. We saw that the normal behavior of them was quite volatile. It changed quite a lot. That was due to low volume, et cetera, et cetera. So before selecting the donor pool, before selecting these values here, to calculate the synthetic control, we had to remove a few variables, like hand-picked variables, because we knew that was not the normal behavior. So that was the way to avoid any big changes in the synthetic control version. So we were happy to see that when we actually calculated, we were happy to see that the blue line was mimicking the orange one quite closely. So yeah, we were confident to say that was a good selection of members in the donor pool.
Thanks for the talk. A related question, actually.
I think your mic is off.
It's on. Maybe I'm quiet. Okay. So yeah, I was wondering if you experimented with using time-dependent weights. I guess here they are just constant once you estimate them. Because I guess like those combinations might also change over time, but maybe it's not necessary. Like maybe.
No, that's a very good question. To be honest, I've never thought about this, because we're trying to minimize the distance between these two curves across all the time. So it's not minimizing point by point. We're doing, let's say, a MSE, a minimum square error between for the entire pre-intervention period. So no, I did not use any time-dependent analysis, but that might be something interesting to consider. Thanks for the suggestion, not question.
What's the time period that you use to determine the synthetic control for this?
So the pre-intervention, so we have years worth of data here. So this is important to mention, this is aggregated data. It needs to be aggregated for the synthetic control. So we have a value per month, and we have several years here of data prior, before the intervention. And after the intervention, we have, I think, a year worth of data.
And do you take into account, obviously, COVID, for example? Is that why there's a dip in certain bits of the curve?
Yeah. So this dip is probably COVID. And there's an important thing as well, that we need to have enough time during the post-intervention period to see the effect of these interventions. So if you're calculating synthetic control, the result of your intervention might just come a few months later, a few years later. So it's important that we have enough time during the post-intervention to clearly see the effects of these interventions as well.
Excellent. Thank you, Matheus. Round of applause.